Pause it. Integrity is on. I will not forget it. Hey, just in time. It just started. All right. So you guys did your first online question assignments. Do you have any questions or anything about those? I guess probably not. The answers were there. That was helpful. I think that's a nice buffer because you'll have your first quiz today, and you know it's always weird to take a quiz first because you have no clue what they look like, what the questions look like. So it's nice to have 10 out of 10 points for the assignment to help buffer with that. Not that I'm like, oh, you're going to need those points. This quiz is so hard. It's not. It shouldn't be that bad. So any questions on how to submit that, to do that? Everybody did it successfully, so that's good. You also did your first assignment. Are there any questions on that specifically or how to turn it in? I forgot to take the please bring a hard copy to class off. So if you brought one, that's fine. But I would love it if you would just email it to me too, because that way I can correct it and send it back to you by Monday. That way, if you did something wrong, I can correct it right away and be like, don't learn it like this. Learn it the right way. All right. So I think, did everybody send me one? No? Okay.
No, I have my hard copy because I wasn't able to figure out how to attach it.
That's what, so is there an issue with attaching? Because I think somebody else was having problems attaching stuff. Is it Mac? That's okay.
So I just took screenshots.
Yes, because
my grabs and then just the boxes and make all that.
Cool, yeah.
And sent those as attachments, which I just got Word on here, so you should be able to see them. But
Cool.
in the email I said, let me know if for some reason you can't.
Awesome. That's what. So. I was going to say tonight I'll look over them and I'll email you and let you know without like taking any points off or anything. You know, like if I can't see it, we'll just figure out how so we can figure out for next time what's the easiest way to do that. I know, I don't know, Dropbox or something. Maybe I can put something in so you can turn them in an Angel. But I think I saw your Word file this time, so I'm totally fine with Word file and screenshots if that's what works.
So email for the quiz and the homework is acceptable?
So for the online questions, you mean?
Yeah.
Or yep.
Sorry.
Yep. I was like, quiz, you'll have a hard copy in class, unfortunately. No, so the things are, well, if you have a phone with a calculator on it, that might help. I don't think you'll actually need one. The numbers I have are so small that you should be able to do them by hand, but if you want to be like, sure, you can use your phone. I know. Hey, Google this. So, all right. So, yeah, I'll take a look at your homework assignments, and I'll get them back to you by Monday, and we'll iron out any problems we have in electronic submission. All right. Any other questions about anything so far? You guys are like, let's get this stupid quiz done. Like, it's all sitting there. I want to get it out.
I had problems trying to make a box plot. I didn't know if I was supposed to go back and start at the beginning to make it because it kept taking me to a screen and I kept trying to label it and all that. And
Yeah.
I never got
Everybody.
I don't know if anybody
I don't
else
remember
had
what
that.
I just kept pushing buttons until it finally worked, but I don't remember what I pushed.
I had to go back, because I remember getting tested and I had to go back and find a different one that's a box plot. But I can't remember.
And so I don't have a box plot on mine because I couldn't figure out what.
That's what, if you want, during the lab tonight afterwards, we'll walk through it. Because sometimes you have to change the variable from, because I think the default is like ordinal, and it has to be scale.
Yeah.
And if you don't change it, it won't let you do it. So it just like doesn't do it. Actually, so we can walk through that and figure it out. Cool. All right, any other questions? All right, let's dive in. Okay, so today, it's a big day. Okay, so what we're going to do, we already have been kind of like asking questions from last week. Then we'll do a brief review of last class. Sorry, like last week nobody was here. Last class. Then we'll do this review, and if you have any questions during the review, let me know. And then after we're done with the review, we'll do a quiz, take a small break, and then we'll start the lecture. And It is like a mother of lectures today. I'm sorry. It will always be better than this one, I think, in the future. But like, so we're going to start, we'll talk about standardization and z-scores and standard error, and those things kind of map onto what we've been doing, and it will be like, oh, this makes sense. And then we're going to dive into inferential statistics and talk about one sample t-test and significance. And it's just like a weird mind puzzle the way you interpret these. So we'll go through it over and over again, and we'll go through some more in the lab, and it's just confusing the way like null hypothesis significance testing is really weirdly worded and confusing. So we'll go over and over it, and if it makes you feel better, most researchers don't completely get this. So like we're just like, oh, p is less than 0.05. Red flag, let's go. Wait, green flag? Anyway, checkered flag. We can go. So we'll go through like what it actually means, and then you'll just know like I need to check this value, and if the value is okay, then I'm okay. But it'll be good practice. Okay, so let's go ahead and do some review, right? So last week we kind of started off talking about samples and population, and the whole point of statistics, right, is that we really don't care about our sample. Not that we don't care about them, but you know, like we really don't care so much about the sample. We're trying to understand information about the population. And it's too hard to sample the whole population, so we just grab a little snippet of them, try to understand them, and apply it to the population. And so the way that we get samples will influence the information that we get, right? So we talked about 3 different ways that we sample. We do random sampling, where everybody in the population has an equal chance of getting into the population. So getting in is completely, or into the sample, getting in is completely random. Then we have representative sampling, right? And that's where we specifically create a sample to have the characteristics that we want, right? So if we want 52% women, 48% men, we make sure that that is represented in our sample. So it's not random, it's completely created, so it works how we want it to work. Then the other way, which is the way that most of us actually use, is a sample of convenience, which is where you just, like, will you please be in my study? Yes, okay, great. And we also learned that all methods have their pros and cons, right? And we kind of talked about how it's a balance of work up front and work on the back end, right? So it's a lot harder to get a random and a representative sample up front. It takes more time, it costs more money, more energy, but it's usually easier to generalize once you have your findings. On the opposite end, right, you have your sample of convenience, which is easier to compile in the first place, but when you're trying to generalize, you might run into some issues, so it might be harder to work with on the back end. So that's sampling. Any questions about sampling? All right, pretty straightforward. We also talked about the 2 main branches of statistics, right? We have descriptive statistics. They really describe the sample that we have, and we kind of spent all last class talking about different types of descriptive statistics, right? So we have mean, median, mode, we have frequency, number of cases. We also talked about measures of variability like range, variance, and standard deviation. These are all statistics that describe the distribution of scores in our sample, right? So we're just describing our sample. In contrast to that, we have inferential statistics, right? And that's where we're taking stuff that we get from our sample and inferring it, trying to see how it, trying to understand the population from it. So making inferences from our sample about the population. And we have to be somewhat confident that our sample or the information we're getting in our sample represents the population accurately, right? And some of the ways we do that is our sampling. We'll talk about some other ways that we do that because the last part of the class will be all about inferential statistics. We didn't really go into that this much, the last class, right? We just mentioned that it is another branch of statistics. But we did say there are 2 types, descriptive and inferential, and we focused a lot on descriptive, which are nice and pretty simple to do. Then we talked about how we can classify variables, right? And one of the ways we can classify variables is by their characteristics, right? So we talked about nominal, ordinal, and scale variables. And this can get a little bit confusing, so I usually think of it as a hierarchy with what you can do with these numbers, what these numbers mean, how much information they have attached to them. So we have our nominal variables, right? These are just numbers that are standing in for names. So remember, nominal, name. And so there's no real numerical value. It's just like 1 is standing in for female, 2 is standing in for male. There's no there's no real numerical value associated with it. Next on up the hierarchy of having more information is the ordinal variable. And this has some numeric properties, right? You can order them. So like, you know that 3 is bigger than 1 or 5 is bigger than 2. So it has ordering to it, but it doesn't have any other numerical qualities. So there's no equal intervals. So basically what you think of is like, so for example, when you're ranking people, somebody gets a gold medal, somebody gets a silver and a bronze. The difference between getting a gold and a silver isn't necessarily the same as the difference between getting a silver and a bronze, right? Like, there's just no real interval between them. We're just ranking them. So you could say this is bigger or smaller, but as far as units in between them, intervals in between them, it's really muddy. So there's no real interval units there. And then next up you have scale variables, and those are any variables that have equal intervals in between them. So honestly, like most of our scales of measurement have this, right? So when we're talking about age, weight, income, number of children, height, temperature, all of these things have interval properties, meaning they have these scale properties. So the difference between 78 and 79 is 1 degree, just like the difference between 76 and 77, right? So like if we're talking about temperature in Fahrenheit, 1 degree is 1 degree across the scale. So the intervals between the units are equal across the entire scale. And the only difference between interval and ratio is that ratio has a true 0, right? So 0 means the absence of something, whereas interval, 0 may not be that meaningful, but the intervals are equal across the scale. Does that make sense? So that's basically, so I try to think of it as nominal is name, ordinal means you can put them in order, but that's all you can do. And then scale is basically everything else, right? All of our good measures with actual intervals that mean something. So that's one way that we can classify variables. Another way that we can classify them is how we're using them in our study, right? What they mean for our study. And so this is where we talk about dependent and independent variables. And so basically when we like boil it all down, typically the independent variable is what we think is causing something, right? So it's the one making the difference, causing the effect. The dependent variable is dependent on the independent variable. So we think that's the one that it depends on the independent variable. So that's how I kind of remember it too. So we had our little example where our research question is whether or not chillax reduced ADHD symptoms. And so what was our independent variable in this? Right, whether or not you got chillax. And then the dependent variable is, yep, ADHD symptoms. So we talked about how we can classify variables. We also talked about how we can classify different types of the research design. And if you printed out your slides, it says counterbalance, but we didn't talk about that, so I scribbled it out, and so this is the new one. But anyway, so we have two main types of research that we do, either experimental or correlational. And so experimental, that's the one, it takes a little bit more work up front as well, but it lets us establish causality. So it really lets us know if the independent variable caused the change in the dependent variable. And so this is where we talked about random assignments to the control group and the treatment group, right, where the treatment group gets the treatment and the control group gets the placebo. And so like for our example, we wanted to treat the groups the same. We wanted to give them both pills so that they would both feel like they're in some kind of a treatment, but we really wanted to see if the drug that was in the pill was working. So we had to assign all these kids with ADHD into two groups, and then we gave the treatment group chillax, and we gave the control group sugar pill to see how they would react. And then at the end, we measure ADHD symptoms, and if they've decreased, we're pretty sure that it's caused by the drug that's in the chillax pill. So that's the experimental design. But we also talked about how there's a lot of things that we can't measure this way. Like anytime we're studying something that has harmful effects, it's really not very nice, it's probably illegal, or impossible to assign them to different groups and have one group get this harmful condition and the other not. So the way that we study a lot of those things is with this correlational design, right? And this is where we look at the degree of relatedness between variables, right? So we just see how much these variables are related. And it's great for allowing us to look at this relationship, but because we don't have any of the characteristics of an experimental design, we aren't sure about causation. So we can say like, you know, the data supports that these are related. And we think, you know, that one might cause the other, but we never know for sure unless we actually do an experimental design. All right, so any questions on any of this stuff so far? All good? All right. Then we also talked about measures of central tendency and measures of variability. And the way we introduced it, we kind of talked about the one with the least amount of information first. It's usually a bit easier to calculate than the rest. But then we end with the one that has the most amount of information included in it, and it's usually the harder one to calculate. But it's also the one that we use the most because it has the most amount of information in it, right? So we talked about mode, and that's just the one that occurs the most frequently in your distribution. The median, right, that was the one that marks 50th percent, so it's the exact middle score. And then we have the mean, that's the average of all the scores, right, divided, so it's the total of the scores divided by the number of scores we have. Then we talked about measures of variability, and we talked about the hated range, where it's the largest value, subtract the smallest value from the largest value, so we know how much difference there is between the scores, but we're not necessarily sure what the smallest or largest score was. It just tells us like how big the difference is. Then we talked about variance, and that really looks at how the scores are spread around the mean, right? How much they deviate from the mean. And it's a really awesome measure, but it's not in the scale that we need. And that's where we go to the standard deviation, which gives us all this excellent measure, all this excellent information that the measure of variance does, but puts it back into units so that we can understand what that means for our scale. So just to kind of refresh yourself, we went through how to calculate the variance, right? And we went through all the steps to do this, and basically by doing that you can see exactly what the variance is doing, right? It's taking the score minus the mean, so you get the deviation from the mean, and then we're squaring those so we don't have negative values, and then we're summing them up and dividing by the number of people in our sample, basically, right? -1. So this is how we got our variance. And integrity is covering up the actual value, but our variance estimate is like 8.5, I think. And then we also saw that the difference between the variance and the standard deviation is that one square root, right? That's the only difference. So the variance calculates it all up for you. It's standard deviation. All you have to do is take the square root of that variance and you get the standard deviation. It puts it back into meaningful units for us. Then we talked about our normal distribution, right? And we talked about how we've got our mean at the center, and if it's a perfectly normal distribution, all three measures of central tendency line right up, right? Mean, median, and mode all on top of each other. And then we have units away from the mean are standard deviation units, right? So plus or minus however many standard deviations. We also talked about how because the normal curve has certain stable properties associated with it, we can infer how many scores are under any certain area of the curve, right? So under this first standard deviation above or below, we know that there's 68% of scores roughly fit under that. And we also know that about 95% of the scores can fit within 2 standard deviations from the mean. Let's see, and we also talked about skewed distributions, right? So that's our normal distribution. It's beautiful. Everything fits really well with that. But sometimes we get skewed distributions. So we talked about positively skewed distributions and how that messes with our probability assumptions as far as they go with the area under that curve, right? So basically, when we have a positively skewed distribution, it kind of changes all of our measures of central tendency and makes it so they don't map on nicely like they do with the normal distribution. And so when we talk about that, remember positive skew is it's pulling everything up, right? And the tail points up. That's how you remember that. And when we look at these, what we tend to see is as far as measures of central tendency go, right, the mode is not affected by the skew. The median is slightly affected by the skew. It's slightly pulled up, but the one that's really affected is the mean, right? It moves much higher up. And then similarly with negative distributions, we have a score that's kind of pulling this down, so the tail points down. And again, mode is pretty much unaffected. Median is pulled slightly down, and the mean is, again, really affected and pulled much, much further down. Let's see. And then, so we talked about that. We also talked about kurtotic distributions. And we didn't go too crazy into these, but we basically saw the same things, that when our probability assumptions are based on a normal distribution, if we don't have a normal distribution, these assumptions fail and they don't work as well, right? So when we have a leptokurtic curve, all the scores are bunched up in the center, and so we don't have like 14% between 1 and 2 standard deviations, right? Everything is kind of up here. And the same with this platykurtic distribution, right? Like we do not have 68% of scores in the middle. We have less than that, and there's more out to the side. So basically all of these probability assumptions, they fail if we don't have the normal curve. So how long did that take me? Look at that, 20 minutes. We could have just done that last week, right? All right, so that's basically everything we talked about. Are there any questions you guys have before we start this quiz? Anything in specific? No? All right, let's do this. All right, I'm going to pause. All right, Tegrity, we just took our quiz, and there's no more questions about the quiz. So if there's no more questions about anything, we'll go ahead and move forward, and we'll start talking about standardization and z-scores. And so, as you probably remember from your textbook, z-scores are really helpful for basically two things, right? When we want to compare scores from a different scale, like ACT scores and SAT scores, they're really helpful for that. They're also really helpful if you want to know about a percentile of scores in a distribution that are below a specific score. So more specifically, like the book said, when you find out that a child's height is in the 90th percentile, this is how they take that child's raw score for height and figure out what percent of z-scores are below that height, right? So if you know that a child is in the 90th percentile for height, that means that 90% of kids are shorter than them. And we'll go through this more and more, but basically just to kind of introduce you to what z-scores are used for, they're used to compare things from different scales, put them on the same metric so we can meaningfully compare them, and it's also helpful to let us see what percentage of scores fall below that score in a z distribution. So that's basically what we're going to be learning in this little mini unit here. And so it's a really good tool for things like this. That's what we're really using it for. But I think the way the book presented the percentile stuff was kind of brief, and in its brevity was kind of confusing. So we'll walk through that a little bit more, and hopefully it'll make more sense when you're done today. But let's go ahead. We'll start with z-scores and what they do, why we use them, how they work. So z-scores, basically, they let us convert a raw score into a standardized score. So basically, when we have z-scores, what we're doing is we're converting scores from different scales to a similar scale, right? So that we can make this more meaningful comparison. So we can compare different scores in a meaningful way. So how do we do this? Let's just start with a little bit of more information on what z-scores are. And what we do when we standardize them to make z-scores. So basically the term z-score, it's just another name for standardizing a score. So z actually just kind of stands in for standardized. So standardization, this is this process of converting each score in a distribution to a z-score. So you'll have this distribution of z-scores with standard deviation units. That sounds really confusing. So what exactly does that mean? It'll become a little bit more clear as we're walking through and looking at examples of it. But basically, we use a formula and we convert raw scores into a distribution of z-scores that has the mean is set to 0, so it has a mean of 0, and all the units surrounding the mean are converted to a standard deviation unit. So instead of saying like the standard deviation is 10 more, it's like 1 becomes a standard deviation. So you have a mean of 0, and all the scores around it are 1, 2, and 3, -1, -2, -3. So in a z distribution, we're just converting the score so that the mean now is a 0, and that's at the center of the curve, and all the units around it are 1, 2, and 3. So it makes it really kind of simple, simplifies it. And the other thing to note is that z-scores with a positive score are above the mean. Z-scores with a negative score are below the mean, right? So 0 is at the center, anything below it is a negative z-score, anything above it is a positive z-score. So knowing that, let's just go ahead and practice kind of interpreting some of these. So if I say I have a z-score of 1.1, what does that mean?
Positive.
Yeah, it's positive. It's 1.1 standard deviations above the mean. That's basically what that would mean. So we'll put that up here for you. I couldn't get the thing, just this to fade in, so it's like I just have to say the number and then put the answer up there. And you guys have the answer, so why don't I just put it up there anyway? It's like if you printed the slides that you have them. Like it's a big secret. Oh, sorry, -1. So if you have a z-score of -1.1,
It's below.
exactly, it's more than 1 standard deviation below the mean. If you have a z-score of 0.3, then yeah, it's positive, and it's not a full, it's just 0.3 standard deviations above the mean. So basically, it sounds a little bit complicated when you just talk about it, but when you see it, it actually simplifies everything. It just puts this on this very simple metric of the mean is 0, the units surrounding it are 1, 2, and 3, and they're standard deviation units. So a z-score is the number that indicates how far above or below the mean a given score in the distribution is, and the distance from the mean is given in standard deviation units. So we'll look at an actual standard deviation or an actual distribution, a z-distribution in a second. But let's go ahead and just look at the formula for the z-score first and see how this conversion is actually done. And so I think the easiest way is to kind of walk through this formula and then go through a couple examples so you'll be able to see exactly what's happening. So to do this conversion, right, we use this formula. And you can see that in this formula what we're doing is we're subtracting the mean from raw scores, and then we're dividing this by the standard deviation. So in this formula, you can see that to get this new z-score number, we're literally looking at how the raw score deviates from the mean, right? So how far away is the score from the mean? And then we're putting it into a metric of standard deviation, right? So that's what we're doing. We're converting that metric. And your book always gives you the formula for to calculate population parameters. And we usually don't ever have information about that, so let's go ahead and kind of ignore that for now and just focus on the formula that we would actually use to calculate a z-score in this class. And we're kind of familiar with some of these terms at this point, right? So this x is the score that the person actually got. The x bar is the mean for the whole distribution of scores that you have. And the s is the standard deviation, right? The square root of that variance. The s is the standard deviation. So that's exactly what we're doing. It's just in the terms that you would use in your statistics book, right? All these little numbers standing in for other things. So let's go through this with an example. And let's say we have some data which has a mean of 100. So we don't really even have to know what this data is. We just know it has a mean of 100. It has a standard deviation of 10. And let's say we have one individual from this distribution of scores that has a score of 115. So if we plug this information into our formula, right, we can see that if we take this score, 115, and subtract 100 from it, then we would have 15, right? And 15 divided by 10 would give us 1.5. So if we plug that information in, this person with a raw score of 115 has a z-score of 1.5, right? All right.
Would you say just 1.5 for the z-score, or would you say this z-score is 1.5 standard deviation?
I think if you were talking and trying to explain it to somebody, you could say this is a z-score of 1.5, meaning that they're 1.5 Yep, but most people will know this is what a z-score is. It's talking about how many standard deviation units you are above or below the mean. So let's walk through one more nice, really easy one. So let's say we have the same exact data, right? We have our mean of 100, we have our standard deviation of 10. Now we have this individual from the same distribution that has a score of 80. And again, we can plug this in, right? And we can take the score of 80 and subtract the mean of 100. Now we have a negative number, right? Negative 20. Negative 20 divided by 10 is negative 2. Or negative 2.0. So then if we were going to interpret that, we'd say this individual who has a raw score of 80 has a z-score of negative 2, indicating that they are 2 standard deviations below the mean, right? Pretty straightforward. So again, when we standardize scores, all we're doing is using this formula to kind of change, like mess the metric up a little bit and make it simpler to interpret things. So we're just setting the mean to 0 and converting the units of measurement to standard deviation units. So let's go ahead and look back at this normal distribution graph. It's nice and familiar. Graph? Yeah, I guess. It's familiar to us. And let's just refresh our memories and kind of go through and fill this graph in again, right? So here is our, anyway, here's our information, right? Giving the answers away. We have our mean of 100, standard deviation of 10, our score of 115, and we know our z-score as well because we calculated it. And here we have the same exact distribution, and now we have our person with the score of 80 and their z-score. So we know the mean is 100. So where does that go on our curve? Right. Look at that, right in the center. I love to make them like fade in and fly up. I don't know why. It's like the only joy I get out of creating these. Other than I get to share all this wonderful information with you guys. Anyway, all right, so we know that the mean is 100. It's in the center. We know the standard deviation is 10. So then what's our value here? 110, right? We can do this. We know all this, right? So we can easily fill this in. And so we did this last week, and we're really familiar with this. Now that we have all this information, let's go ahead and just put our people in on this, right? So we have the first person with the score of 115, where are they going to go? Right. Totally, like not a trick question, right where 115 would be. And then where's the person with the 80 going to go? With 80. Seems like a really ridiculous question. And so what's kind of cool is you can already see that, so here's all of our raw scores, right? And we're on this raw score metric. You can already see that this person with the score of 115 is 1.5 standard deviations above. And this person with a score of 80 is 2 standard deviations below the mean, right? So let's go ahead and put our z-scores on here. So when you have a z distribution, this is what it looks like. So here is your mean of 0. Here is your standard deviation units, right? So it just totally converts the raw score, the scale, to a simpler scale. And I just wanted to show it to you that way because you'll basically see that it is exactly like we're not doing anything except for changing the metric and making it simple. So we know this person has a raw score of 115, 1.5 standard deviations above. This person with 80, -1, -2, and our mean is at 0. So all we're doing when we convert z-scores is convert the score to this scale. And usually we will actually keep things in our raw score form because that tells us more information about like our scale and it's actually more useful for when we do most statistics. But anytime you want to be able to compare people that have scores on different metrics, this is a really useful way because it's going to put both of them on this same scale so that you can compare them. So let's go ahead and look at that. So when we want to compare different metrics, we can use the Z-score to help put them both on that metric, and then we can compare them more meaningfully. So like your book had the excellent example of ACT and SAT scores. Because when you think about these tests, they're basically measuring the same thing, right? Like they both have like an analytical and a like a more qualitative or like verbal section, right? They're both measuring college readiness is basically what they're looking at. The big difference between them, I mean, I'm sure there might be other differences. I'm not an expert. But one of the differences we know is that the ACT score theoretically can range from 1 to 36, right? And the SAT score can theoretically range from 200 to 1600, right? Yeah, double 800s. I don't know anybody who's gotten that. But so let's just say that I'm applying to a college, right? And I have an ACT score of 23, and I'm actually feeling pretty good about it. But my friend who's going to this East Coast college that I want to apply to, she's telling me that she got in, but that she had a really hard time getting in, and she had an SAT score of 900. If I want to compare these, right, what I need to have, I have my score, I have her score. I need to have the mean, so the average scores for these tests. So I need to know what the mean ACT score is and the mean SAT score is. I also need to know the standard deviations of those scores, right? So how much they typically vary around that middle score. And luckily, usually you can find this information online. Half the time, like the ACT website should have that information available to you. Same with the SAT website. If they don't, that seems problematic to me. But anyway, we'll pretend that you can just log right in and there it is. So all we have to do is get the mean and standard deviation, and then we can use the Z-score formula to convert these scores, right? So let's say I do that and I find out that the ACT has a mean score of 18 and a standard deviation of 5, and that the SAT has a mean score of 1,000 and a standard deviation of 100, right? And here's our formula for our Z-score. So if we actually plug in these numbers, we can see that for my ACT score, I get a Z-score of 1. So I'm 1 standard deviation above the mean. That's pretty nice. For her SAT score, oops, put that up there. There we go. For her SAT score, she has a Z-score of -1. So she's actually 1 standard deviation below the mean. Yeah?
Should I say 23 minus 18?
Yes, it should. Oh, thank you. Darn it. 23 minus 18 divided by 5. So yeah, you can see these Z-scores, and so like, although my meager score of 23 sounds less impressive than 900, we can compare these on this meaningful, similar scale, and we can actually get an idea of how they relate to one another. And so I can see that my score is actually better, right? It indicates more college readiness than her score maybe does. And so I could apply to that college. There's no guarantee I'll get in, but I wouldn't let my ACT score stop me, right? I'm actually doing okay. So that's one benefit of the ACT score, of the Z-score. You can compare these meaningfully. Are there any questions about using it this way? All right, let's move on to these kind of funky percentiles. So, right, the other benefit of the Z-score is that they let us know what percentage of the distribution of scores fall below a raw score, right, or below a Z-score. So if I want to know where my raw ACT score, raw sounds so raw, my raw ACT score falls compared to the rest of the distribution, I can use my Z-score and this table of probabilities associated with Z-scores in that area of the curve, and I can find out what percentage of scores typically fall below my ACT score. So if these scores come from a normal distribution, right, because everything's kind of predicated on having this normal distribution, if my ACT scores come from a normal distribution, I can use this Z-table, which is basically, it's just a table full of probabilities associated with Z-scores, and I can use that to kind of compare my ACT score and see how many other scores fall below it, right? So to do this, I need to take my z-score and compare it against that table that has all the probabilities associated with area under a normal curve based on the z-score I have. So again, that sounds like a lot of words, but let's go ahead and do that. So I have my standardized ACT score. We already figured it out, right? I have a z-score of 1. Figured that out on the last slide. And it's a positive z-score. So all I have to do is go and look it up in that table. That's really all I have to do. In your book, it's on page 185. It's Appendix A. You totally don't have to look it up, though, because look, I found a digital one. So we'll just use this one. It should look very similar to the one that you have. So to use this z table, you have to find your z-score, and basically what you'll see is part of the decimals for your z-score are over here on this column, and the second half are over here on this top row, right? So I have a z-score of 1.00. So I have to go down on this part to the beginning, 1.0, and if it was 1.06, I would go over to 06, but it's 1.0, that's really nice. So there is, I think I even circle it. Yeah, there we go. That is the probability associated with my z-score. And so, I'm going to get over here. So the number associated with this z-score is 0.8413. And so the next step we have to do is convert it back into a percent. So here's my 0.8413, right? That's where I got that value, is from the table. And then I convert it back into a percent, so I just move the decimal places over to. And basically what this is telling me is that 84% of scores, of ACT scores, fall below my score. So I'm in the top 84th percentile, and I feel, again, pretty good about myself. What's nice is if you remember the normal distribution, you can totally see this, right? So you remember the mean splits this distribution in half, so 50% of scores are below, 50% of scores are above. My z-score is 1, that means I'm 1 standard deviation above the mean, right? And we know that 34% of scores fall, roughly 34% of scores fall between the mean and 1 standard deviation. So if you just add this up, do I add it up? No, darn it. If you just add it up, you can see that it is 84.13% of scores fall below me. So it's cool, like you can actually see it map on like that. So that's why that works that way. And unfortunately, the table in your book and a lot of the tables only have positive z-scores. So if we have a negative z-score and we want to know the probability or the percentage of scores that fall below that, we have to do a few more steps to calculate that. So let's go ahead and look at a negative z-score and see how we'll do that. Because I don't know about you guys, but I was reading how to do it in the book and I was like, what are you talking about? And so I went through it like 5 times and I was like, I totally get it now. So I had to break it up into little steps because that's how I do things. What do I do first? Then next, then next. So here's our negative z-score. And so if you have a negative z-score, you basically have a couple more steps. The first step is you have to look up the absolute value of the z-score on your table, right? So basically, here's our table. Our z-score is negative 0.26. Absolute value would be 0.26, right? So if we want to look this up on the table, right, we go to 0.2. And then we go over to 6. So when you add that together, you get 0.26, right? And so I'll go ahead and circle that there too. So the probability associated with this z value is 0.6026. So let's go back here. So you can see right here, if we convert that back into a percent, the percent is 60.26%, right? So if this was a positive z-score, it would be that 60.2% of the scores would fall below it. But this isn't positive, right? And when you look at this, you can see that like fewer than 50% fall. So there's something a little wrong with this score. So we have another step. And basically, to find the actual probability, all you have to do is subtract this score from 100. So 100 minus this probability will give you the actual probability associated with your negative z-score. You can also find negative z-score tables online. That's very helpful. If you were doing this in SPSS, it would give it to you. You wouldn't have to look it up or do this calculation. But let's say you're stranded on a desert island and all you have is your appendix. And this is how you would figure that out. And everybody would be like, you need to help us find food. So the steps for this are like, if you have a negative z-score, you need to look up the absolute value of the z-score, get that probability, convert it back into a percent, and then subtract it from 100. So I don't know about you, but I was just like, this book makes it, I don't know, made it seem much more difficult than that in my head. And I was like, oh, let's just break it down. All right, the last thing we'll talk about as far as z-scores go and these probabilities associated with these scores, you can find the percentage of scores that fall between two scores, right? And doing this is not much different than what we've just done. So we're just adding one more step to what we did. So let's say we want to know the percentage of scores that fall between a z-score of negative 1.03 and a z-score of 0.56. So the first step is to find the percentage of scores that fall below the score furthest to the right, or the highest score. I don't know, I'm like, why do I have to say furthest to the right? Just take this top z-score and go to the table and find the probability associated with that, right? And so I did that. We don't have to go back to the table because we know how to use the table, basically. But if you looked up 0.56 on your z-table, you will see that it's associated with a probability of 0.7123, and we convert that to a percent, move the decimal over. And so basically what we're saying is 71% of scores fall below a z-score of 0.56, right? But we need to know like how much of this we need to take away, right? Because we don't care about just how many fall below. We care about how many fall to here. So then the next step is to find the percentage of scores that fall below the lowest score, right? The one closest, as the one farthest to the left, but it's your lowest score, right? And again, this is a negative score, so we go through all of those steps. We take the absolute value of the negative score, so we go and we look up 1.03 on the table, and when you do that, you'll see that that's associated with a value of 0.8585. Then we convert it, I should say 8485, I'm sorry, 8485, and then all these little numbers. And then you move the decimal over, right, so you've got your percentage, and that means that 84% of scores are associated with that absolute value, right, with that positive value. We know it's not right. There's way fewer than 80% of scores, so we have to take this score, we have to subtract it from 100, right? And that will give us the probability associated with that negative 1.03. And so after doing all those calculations, you can see that 15.15% of scores fall below negative 1.03. So you use a little bit of like, I don't know, like common sense. That sounds so mean. But you know, like if you get a z-score and you're like, or the probability associated with it and it seems wrong, it might be because you need to subtract it from 100 and then it will seem right, right? So just like step through and look at it meaningfully. All right, so now we've got the a number of scores that fall below this. So if we want to find out what falls between these two scores, all we have to do, right, is subtract that piece. So that's the last part, is you take the percentage of the, it sounds so convoluted when you say it like this, take the percentage of z-score furthest to the right and subtract the percentage of the z-score to the left. But basically you're taking the high z-score and subtracting from it the low one, right? And that will just tell you how much this accounts for. And so when we do that, we can see that if we take 71.23 and subtract 15.15 from it, you get 56.08. And so that's basically saying that about 56% of scores fall between these two numbers. All right, any questions on this? Z-scores. Now you guys know everything you need to know about z-scores, more than you ever wanted to know, right? I just wanted to go over them because I thought the way your book presented them, I was like, I find this confusing, and maybe if we just walk through it, it won't be so confusing anymore. It'll be way more information than you want, but you won't be confused anymore.
So on this last one you just did, where did you find that? You said 1.03, so I would come down to the 1,
Right.
then go across and find the 0.03 at the top.
Yep,
And
exactly.
match them up. And that, what number is that?
It should be,
85?
is it 84, 85?
84, 85.
That's it. Yep,
Okay.
that's it.
Okay.
And then because it's negative, you have to subtract that from 100. I don't know why it took me so long to wrap my head around this. It's like, why is this so
So you
confusing?
find the percentage of vote and just subtract them, and that's your answer.
Mm-hmm. That's exactly it, right? Like, in short, you should totally teach this class. Just be like, this is all you have to do.
No, you explained things very,
But
very
it
well.
doesn't say why.
Right. All right, so that's the z-score. And again, I just found that very confusing, but after walking through it 15 times, I was like, I totally know how to do this now. It's just find it on the table and then convert it to a percent or minus, take it from 100, take it from another z-score, take it from another z-score. All right, so all these examples that we were just talking about, they present like the very handy use of z-scores for either understanding how to compare things from different metrics or how to compare like percentiles underneath a score, right? Like how many fall below. But again, all of this is based on the assumption that you have a normal distribution of scores. And so, again, the last thing to kind of note is that if you don't have a normal distribution of scores, none of this works that well, right? It doesn't work anymore. And so I want to just kind of walk through it a little bit with you on a non-normally distributed scale, or score distribution, so that you can see why that is. So if you have non-normally distributed data, right, so if it's skewed, if it's kurtotic, that's so fun to say, if it's kurtotic, basically you can still calculate a z-score using that formula, but you can't use the table of probabilities associated with that z-score to see what percentage of scores fall below the z-score. So, for example, like this non-normally distributed data came from a table in your book, and you can see that we have the mean, we have the standard deviation, but so we can calculate a lot of stuff associated with the z-score. And if we do that, so if you remember the formula for z-score, if we do that, you'll see that a score of 8 here is associated with a z-score of 0.54. And if we go and look at our table of 0.54, that z-score is associated with the number 0.7054. And when we convert that to a percentage, we get 70.54% of scores falling below that. So here's our little curve. And if you look, that is not true, right? Like 70% of scores don't fall below this. 100% of scores fall below this, right? Like there's no score higher than this. So again, you can't use that table. It doesn't work. It's based on normally distributed data. And so what you can do, the only real thing you can do in this case is find the median. So if you find the median, that marks the 50th percentile of scores, right? So 50% of scores are above the median, 50% are below the median. And that's about as close as you can come to it then. If you need to look at percentage of scores associated with the z-score, and you have this kind of skewed data, don't look at the table. All you can do is really calculate the median. All right, any questions on that? All right. Oh, who wants to talk about standard error? This is what you were all waiting for. 6:20. We're doing good. We're doing good. Okay. So that's z-scores. Let's talk about standard error. In the last class, let's put it in context, sorry. In the last class, we covered how to get representative data, right? We did that with like looking at samples and populations and different sampling methods. So we covered that. We also covered how to describe our sample characteristics and our distribution of scores. So we talked about how to look at measures of central tendency and measures of variability. Then we looked more closely at distributions, right? So we covered normal distributions and how all of our probability assumptions are based on this distribution. And we saw that probability assumptions based on normal distributions fail when we don't have normal distributions. Now we just covered z-scores, and we saw that the z-scores have a lot of the same properties of all that stuff, right? So they have a lot of the same properties as raw scores. All we're doing is converting these scores to a different metric so that they have a mean of 0 and their standard deviations are the units around the mean. And so this puts even really different raw scores in the same metric and allows us to look at a z-score and compare it against a table and find out what percentage of scores fall below that. So that's like everything we've done in the course so far. And all of this information, whether you realize it or not, has been really helpful in setting the foundation for inferential statistics, and more specifically looking at significance testing, which is what we're going to end with today. And we'll move into that method of like testing our data and answering questions and making inferences. We'll do that at the very end of the class. But there's one more thing we have to cover before we can do that, and this is this idea of standard error. And the standard error lets us really, like, basically what it's doing is it's letting us know how much confidence we can have in the statistics that come from our sample. It tells us how much confidence we can have that our sample is representative of the population, and it gives us an idea of how much error might be associated with the scores that we are getting from our sample. And all of this will make more sense by the time we're done with this, but I just wanted to introduce you to why the standard error is so awesome and what it can tell us. So the standard error, it's just an estimate that basically lets us answer this critical question. When I get statistics based on my sample, so like for example, if I get the number of average pastries eaten by coffee shop employees, or if I get the average shoe size of U.S. women, if I get a statistic based on my sample, how much error can I expect to have in this estimation? So what is the standard amount of error associated with my statistic? So this is why this estimate, this standard error value, this is why it's so important. It's giving us this critical estimate of the standard error in our statistic, how much error we have in that. So that's what it is. How does the standard error estimate this? What is it based on? We'll get a bit more into that as we walk through it. But let's talk a tiny bit more about what it is. And so at first this will be very confusing, and by the end of this section it will make a lot of sense. But your book says, and it's probably smart, it's like just repeat this to yourself 10 times. The standard error is, in effect, the standard deviation of the sampling distribution of some statistic. Right? We got that, right? Class dismissed. So yeah, not so helpful right now, but if you know that's what it is and you just take it with a grain of salt, then it will make more sense as we go forward. But technically, the standard error is the standard deviation of the sampling distribution of some statistic. And as such, then, it represents how much random variation we would expect from samples of equal sizes drawn from the same population. All right, let's go to an example so this makes a lot more sense. And we'll use our familiar example. So I kept these definitions up here so you can keep remembering them and comparing them and thinking about them. But remember last class we looked at pastry consumption and it was delicious. But we took this random sample of 5 coffee shop employees, and we asked them how many pastries on average do they eat during the week that they work. And we saw that some ate 1, some ate 2, some ate 3, and somebody ate 8. And they are my hero. So we have random variation in this sample, right? Like not everybody has the same score. It varies. It's a little random variation. And so some of the random variation in the sample is probably similar to the random variation in the population, right? Like the population will probably have varying amounts of pastries that they eat. However, some of the variation might be due to the sample that we randomly got, right? So some of the variation is real, some of it is a little contrived, like it's really reflecting our sample and not the population. So maybe our process of randomly selecting coffee shop employees just by chance gave us, in this sample, a sample of coffee shop employees that are on an extreme end of the scale. Like this sample, for whatever reason, does not eat that many pastries, and most coffee shop employees probably eat more. So maybe the actual population value is closer to 8, but we don't know that based on our sample because this is a sample we got. So basically what we need is some way to say how much of this is really representative of the sample or the population and how much of this is because of the sample we got. And so one way we can figure out how much of this random variation is about our sample and is about the population, one way we can do this is keep getting more samples. So let's say I take another random sample, and this time I ask 5 more, and they say 3, 4, 5, 7, and 10, right? So now we have a whole different mean. So the first time we sampled, we saw average pastry consumption was 3 a week. This sample tells us that average pastry consumption is more like 6 a week. Let's say I get another sample, and this sample is telling me that average pastry consumption is about 4.5 pastries a week. So now we have these 3 random samples, right? And they all have 3 different scores associated with them. They all have 3 different average scores of pastry consumption. So if our samples are all randomly drawn from the same population, they all have the same number of participants in them, but they can each give us different information, how do we know if our sample closely represents the population, right? How do we know which one of these samples is more representative? And one way to figure this out is to look at the standard error, or the standard way our statistic deviates from the sampling distribution. Let's talk about the sampling distribution, because that's the first time I said that word. So the sampling distribution, we'll talk about that, and then we'll see how our estimate of standard error tells us how closely our sample information represents this distribution, or this population information. And so sadly, we're going to go away from the pastry example, and we're going to go to the boring example that your book gave of average shoe size, because it's something we can all relate to. Here's a side note. I talked to a girl who works at a coffee shop last week, and she said they get 1 free pastry a day. So I'm just saying, if you work, right, it's way closer to 5 or 8. Yeah. And I'm just saying, I worked at a coffee shop, and I was poor enough that I ate mostly pastries there, so it was probably more like 15. And it was kind of awesome, but also kind of sad. Anyway, my life was great, but here I am. No, so we'll go back to shoe sizes, and we'll kind of simplify it again by looking at, instead of looking at the whole U.S. population, we'll look at average U.S. women's shoe size, or average Omaha women's shoe size. So let's say in this example, we're trying to estimate average shoe size for women in the Omaha area. So what is our population then, right? It's just women in the Omaha area. So we're not trying to take this sample and put it onto the rest of the U.S. population. We are saying we just care about Omaha. That's the only thing we care about. And so to make things a little bit simple and to help us kind of examine the difference between our sample and the population, again, let's just pretend we actually know the population parameter, right? We already know this. And that way, we'll be able to compare it with our sample and see how different they are, right? So let's say we know the average woman's shoe size in Omaha is 8. So the average woman wears an 8. So let's go ahead and look at what happens when we randomly sample, we'll say 20 women in the Omaha area, and we ask them about their shoe size. So here's one random sample of 20 women from the Omaha area. We ask them, what shoe size do you wear? And and they give us, the information they give us gives us a mean of 8.07. That is really close to the population parameter, right? That's like 0.07 off. In fact, I don't even know how you get that. What shoe size do you put in to get you to 0.07? But anyway, that's what SPSS gave me, so we're going to go with it. So I would say that the random variability in this sample pretty accurately reflects the random variability in my population, right? It's really close. So it gives us a pretty good estimate. The sample gives us a pretty good estimate of average shoe size in the Omaha female population. All right, let's look at another random sample of 20 women. And this time, this one gave us a mean of 8. And that's like a perfect representation, right? So again, we can feel pretty confident that the random variability in our sample matches very well with the random variability in the population. So it's probably not something about our sample that's giving us this information. It's probably really reflective of the population that we're drawing from. So let's look at another random sample, mean of 7.5. Still feeling pretty good, but it's a little farther off, right? Here's another mean, little higher. Here's another mean. So basically, what you're seeing here is that every time we randomly sample from a population, we'll get variability in our scores, right? And so that, and some of the variability in our scores will match on to the variability in our sample and will be indicative of what's happening in the population. Sorry, I meant population. So some of the variability in our sample will match onto the variability in the population, but some of it will be characteristic of our sample, right? So it will, the variability in our sample will actually just reflect the specific characteristics of our sample. And so there's usually going to be some error, a small amount of error in the estimates that we get from our sample. All right. If we keep going and going and going, and we have 20, we keep randomly creating 20 samples of 20 Omaha women. So now I have, that's confusing. I have 20 samples of 20 Omaha women. So what is that, 400 women? And so I've done this, I've asked them about their shoe size. We keep seeing that each sample will give us slightly different information, but they're all kind of close to that 8 that we got in the population. So like your book says, this is like the first step in totally getting standard error and what it's doing. Once you realize that different random samples of equal size can produce different mean scores on some variable, like different average shoe sizes, the next step in conceptualizing standard error is pretty simple. If we take these 20 different random samples of Omaha women, each consisting of 20 participants, if we take these samples and their means and we compute the average shoe size of each sample, if we put these average shoe sizes from each sample on a distribution, they will form their own distribution, right? So this is, again, it's nice, it's kind of familiar. We've seen this before. So in this distribution, this is the distribution of the means we got from each repeated random sample. And this distribution is called the sampling distribution. So anytime you have like a distribution of a statistic from a sample, it's the sampling distribution. And because it's a distribution of means, we call it the sampling distribution of means, or the sampling distribution of the mean. So again, we've seen this image before. We're familiar with the normal curve. And so instead of having a distribution of scores with a mean at the center and standard deviation units around the mean, now we have a distribution of means from our samples. And instead of having a mean at the center, we have what's called the expected value of the mean. So it's basically the mean of the sampling distribution, and theoretically, it represents the population mean. Because if you keep sampling and sampling and sampling and you take all the means from all those samples and average them, we should be pretty close to the population mean, right? So, for example, if you don't have the population mean, a way that you can try and get it is if you have a number of random samples and you take the mean of those samples. Then you're getting really close to the mean of the actual population. Does that make sense? Yeah.
Would you say that that's like the mean of the means?
Yeah, it totally is. It's the mean of the means. Yeah. But yeah, so like when you think about it, theoretically, it should, so we call it the expected value of the mean, because we expect that all these multiple random samples, if we average all their means, we should be getting pretty close to the real mean, right?
Is there a certain amount of times you have to do that? Like you chose 20 on this one. Is it always 20? Does it change?
It probably, so I will tell you, as far as I know, a lot of this is theoretical. And people have, there's like statistics institutes where they test these things. I think there's one called the Monte Carlo studies, and they actually test this. So I will say that you don't have to even know that. You just have to know theoretically, if you keep sampling, at some point it will. Exactly. So you'll have some out here that are a little bit more extreme, probably saying that you got a few more extreme people in your sample just by chance, and you'll have some on the same here. But most of your samples will kind of accumulate right here in the center like usual, because again, it's all random, chance. And since this is kind of a law of most things in nature, it will follow the same distribution. Here's another random tidbit. I went and saw Dr. Neil deGrasse Tyson speak, and it was like a day after we talked about the normal curve, and he had a normal curve in his talk, and he was like, this is the Gaussian distribution, and most things follow that. I was like, yes, we just talked about that. So anyway, so yeah, so this is no different. It also will follow that. So we have this expected value of the mean at the center, right? This is the value we would expect the population mean to be, and it's based on all of these samples, the means of all these samples. It's getting really close to that. So that's what we have at the center. And so instead of having standard deviations out here, now we have standard errors. We finally got to standard error. So this in the middle is the expected value of the mean. And basically the standard deviations from this are called the standard error. So you can see it right here, standard error. So the mean now in this distribution is the expected value of the mean. The standard deviation is now the standard error. And so let me say a little bit more about this. So the standard error, like the standard deviation, this is the average or standard difference between the expected value of the mean and an individual sample mean. Right? So this is how much, here's our mean. The standard error is how much your sample mean deviates from this expected mean. So it's just like mean and standard deviation. That's how we interpret it. So this is literally telling us, I wrote to myself, hey, this is the value we expect the population mean to be, and this is how far your mean from your sample is away from that expected mean. So this is the standard amount of error you can assume your statistic from your sample has. So this is the standard way that your statistic or your mean deviates from the sampling distribution. All right, does that make sense?
So when there's 8 up there, should it technically be 8.05?
Yes.
Okay.
Darn it, that is so confusing. I wonder, can I look at that? That's way better, right? I'm so glad that came off. Stop, Integrity! No. That didn't happen. Oh yeah, I use this thing, right? Yeah. You get it.
Yeah, we got it.
8.05.
My God, I'm so glad you guys said something. I would have left there and had a huge red streak. I was like, I don't know how that happened. Check the transcript.
What is this for, though? What is standard error for?
Okay, this is awesome because, well, it's not that awesome, sorry. This is awesome because we will use it in our inferential statistics because it's basically giving us this estimate It's indicating how reliable our information is, how much error is in the statistic that we got. So it really tells us how much confidence we can have in the statistic that we got, right? So if you know that, like, if you have a small standard error, it means you have a small amount of error in your sample, right? Or that your sample mean is close to the expected mean. If you have a large standard error, that means that your sample mean is far away, right? It has a lot more error associated with it, that it's far away from the mean we expect the population to have. So it's a really cool foundation to understand because we'll use it in all of our inferential statistics. It goes in to help us calculate these things and let us know what is the probability that what we got in our sample is accurate.
Is there a certain number that says it's too far away?
That is a great question. I think I was going to get to that next. So yeah. Let's
Okay,
see.
that's fine.
No, and actually, so when I see it in my notes, I'll just skip it. Basically, as far as I know, there might be a rule of thumb out there, but your standard error estimate is going to depend on your sample, on your sampling distribution, on your, it'll depend on a lot of things, but a rule of thumb is smaller is better. That's really, because like if you think about it, if you have, if something you're studying is highly variable, you will expect scores to be spread around. And then it's okay to have a larger standard error because you expect them to be farther away. But if you're studying something that's really close, has a distribution that's really close, if you have a huge standard error, that would be bad. So it's really kind of dependent on what you're studying. So if you are familiar with the typical standard errors of the things you're studying and yours is way bigger, then you might want to look at your sample. Yeah. And you won't have to know that. But yeah, rule of thumb is smaller is better, right? Because it basically is saying there's less error. All right. So we're kind of getting this. This brings us back to that technical definition, right? The standard error is, in effect, the standard deviation of the sampling distribution of some statistic. So this is our sampling distribution of some statistic, and the standard error is basically like the standard deviation. Right? So that makes more sense now. And in this example, because our sum statistic is the mean, this is the standard error of the mean is, in effect, the standard deviation of the sampling distribution of the means, not just some statistic. So what's weird, or what's kind of cool to know, is that every statistic has one of these. So the mean has its own sampling distribution of means, correlation has its own sampling distribution of correlations. All these things have their own distribution. But the principles are all the same. If you calculate a statistic based on multiple random samples, they will all give you similar information. They'll form their own little distribution, and your standard error will be how much error that statistic has based on your sample compared to what we would expect the population value to be. All right, yeah.
This makes complete sense with how you're explaining it, but I'm just kind of like following
Yeah.
along with the homework just to make sure I'm understanding this for the assignment.
Nice,
When it
look at
says
you.
calculate the standard error of a sample with a standard deviation of 122 and a sample size of 148, I'm like, I don't even know where to start now.
Right.
After you
Don't
explain
worry,
it.
because we will get there, because, again, this is beautiful theoretically, like, oh, we have the population mean. We can totally just look at that. Usually we have to use a formula to do it.
Okay, so there is a
Yep,
formula.
so there is a formula. So let's see, yeah.
I must be getting ahead then.
No, you're good, because that's awesome. That's what it's like, Alicia, we should probably go. So yeah, that's funny. That's the bottom note of this page, is that if we actually have all this beautiful information about population parameters, we can, and we can just sample and sample and sample and sample, we can create this distribution. We can look at it like that. And that's very convenient for illustration, but in reality, researchers don't usually have that, right? We're usually trying to get, we have our sample, and that's the information that we have. So we can't just figure out how our sample information fits the population information in this way. we have to be able to estimate it from a single sample. And this is how we would estimate it from a single sample. So this brings us back to this, our first sample of the shoe size of 20 Omaha women. So just like when we were talking about average drive time in class, we had like the actual population parameter, we could compare it. We had that in that instance, but we usually don't have this information. So we have to be able to estimate it. We have some rules that we follow to help us get accurate information, and we also have a formula. So we'll go through the rules really quick, and then we'll go through the formula. So basically, as your book notes, to answer this question, when I get a statistic based on my sample, how much error can I expect to have in this estimation? What's the standard error associated with my statistic? To answer this question, we have to look at a couple characteristics of your sample. How large is your sample, and how varied are the scores in your sample? So we'll look at both of these. So first, let's see how large our sample is and how that affects our standard error. So these rules for sample size and variability around the scores, these come from the central limit theorem. And all you have to know is that this is a theorem that states that as the sample size increases, the sampling distribution of the mean becomes increasingly normal, regardless of the shape of the distribution of your sample. So the more people you have, the more normal your distribution will look. That's all this is saying. And so therefore, if you're repeatedly randomly sampling from a population and you have a decent sized N, a decent sample size, this theorem says as long as you have 30, you should be okay. We are not going to question that. We're not going to ask why. We're just going to say, yep, 30. Sounds good. Thank you, central limit theorem. They're saying as long as you have a sample size of 30, the distribution of the means will form a normal distribution even if the samples are taken from a population with a non-normal distribution. So basically, this is cool because what it's saying is that as long as you have a big enough sample size, you will have a normal sampling distribution, like the one we just saw that has the nice curve to it. And it's important because to determine the probability of the statistics that we have from our sample, to determine whether these are a reflection of chance characteristics of our sample or a reflection of actual things that are happening in the population, to determine these things, we compare our scores against a probability distribution, right? And this probability distribution, like everything else, is based on a normal distribution of sampling means and the sampling distribution of the mean. And like we saw in last class, if we have these assumptions based on that normal distribution and we don't have a normal distribution, the assumptions fail. But this is the beautiful part. Because larger sample sizes will always more closely approximate the population mean than smaller ones, you can use most statistical tests without knowing the distribution of the population if you have a decent sized sample. So basically all I'm saying here is that as long as you have a sample size of about 30, you can be pretty sure that your statistics will follow those assumptions. So you'll be okay. Right? So we can all get to sleep tonight. So as long as you have, and I'm not capable of explaining why, but that's just the central limit theorem, and that's how it works, so that's awesome. So I'm not capable. You guys totally are not expected to be capable of understanding why that happens. So one rule given by this central limit theorem, that's what that theorem is saying, one rule that falls from that is that the larger samples we have will give us better estimates of our statistics. Because larger sample sizes assure that the sampling distribution of the mean is normal, and so these samples will provide us with a more reliable test of whether this statistic is valid. So basically, the larger sample size you have, the smaller standard error you will have. Like put simply, large sample sizes make smaller standard errors, just as a rule. And part of that's because the larger sample you have, the more that sample will look like the population, right? If you have 3 people in your sample, they could be from anywhere in that distribution of scores. If you have 100 people in your sample, you're going to start getting people from all parts of that distribution. So it will more accurately reflect the population. And then, yeah, of course, the larger the sample you have, the more the sample means will start to look similar to one another, right? Because they're all reflecting the same population. So they'll all start looking closer together. So again, you'll have a smaller standard error. So basically, larger sample size, smaller standard error. That's a good thing, and that's what we want. Another rule of thumb is the smaller the sample standard deviation, the smaller the variation of scores around the mean, and the smaller the standard error. So let's walk through this a tiny bit. So again, if we imagine this highly variable population where you have students who score from like let's say we gave them a test and scores range from 60 to 240. That's a huge range of scores, right? If we take a small sample, again, like if we sample 5 people out of that, will that like really reflect the mean of the population? Like, right, maybe, but maybe not, because they could be from anywhere in that distribution, right? But again, if you have a large spread of scores, as long as you have the larger your sample, the more representative of that range it will be. And it's nicer if the scores are a little bit smaller and spread closer to the mean, but as long as you have a large sample, it's okay, because you'll get people from all areas of that distribution. And let's see, what's the next part here? Right, so this, if you have large variability, you basically need a large sample to account for that, right? If you have small variability, so let's say you give a test and the scores range from 93 to 97, then if you grab 5 people out of that distribution, will their scores be representative? They'll be closer, right? Because they can only give you 93, 94, 95, 96, 97. So even if you got like scores that were like 2 93s and 2 97s, you're going to get close to that mean, right, of like in between 93 and 97. So basically what the central limit theorem is saying is that if you have a small standard error, if you have a small spread of scores around that mean, then even small randomly selected sample sizes will have similar means, because they're all going to look very close to, they're all going to be squished in like that. So again, basically the rules of thumb, so having the smaller variance in the population will help reduce standard error. But even if you do have a lot of variance, as long as you have a large population to account for that, or a large sample to account for that, you'll be okay. So just like we had rules of thumb to kind of guide our sample selection so we get a sample that best represents the population, we also have these rules to follow that help us be more confident that our stats, the statistics we're getting from our samples, accurately represent the population. So again, take-home message, 2 main rules of thumb: have a large sample, have a sample with smaller variance if you can. All right, so we have these rules of thumb. This will help us. If we follow this, it helps us get smaller standard errors. It's good to try and do that. So we have those rules of thumb. We also have this awesome formula that we can use to calculate the standard error. So if you don't have time or money to randomly sample all these samples and put them into a distribution, we can use some probabilities from our kind of stable probability distributions to figure out what the standard error would be based on your sample characteristics. So here's the formula for calculating standard error. And when you look at this formula, especially this one because we're a little bit more familiar with these statistical symbols, you can see that it takes into account exactly those 2 things. It's like literally looking at how spread your scores are, the standard deviation, how spread these are, and how many people you have in your sample. So like those are the 2 main things we care about, and those are the 2 main things it takes into consideration. So it's kind of cool that they map on very nicely like that. So as usual, your book gives you these 2 equations, right? And we can ignore this formula for the population parameter because we don't usually have those. If we did, why would we calculate statistics at all? But basically, what you could see is that the only difference between these 2, right, is the symbols. They're doing the same exact thing. It's just, are your numbers based on your parameters, or are they based on the statistics from your sample, right? So we'll go ahead and focus on this one. And if you look at the symbols, yeah, we have S of X bar. And this is the symbol for standard error. And you can kind of hopefully remember it because like S is like our standard deviation, right? So S is like our standard deviation, but the X bar reminds us that this is the standard error of the mean. So there's a little X bar down there that's like mean. So it's like the standard deviation of the means. But so this is our standard error, and we already talked, this is our standard deviation. This is our N, the number of people we have in our sample. And so yeah, you can literally see that we are taking how spread the scores are around the mean and dividing it by the number, how many people are included in our sample, right, or an estimate of that. So let's go ahead and calculate this for our sample. So we have our 20 Omaha women. We have their shoe sizes. When we put them together, they gave us that mean of 8.07 and a standard deviation of 1.94. So here's our 8.07, standard deviation 1.94. When we put this into our formula, right, here's our standard deviation. It's divided by the square root of our sample size. And when we do that, you get 0.43. So that's a pretty small standard error. It's like not even one standard error. So it's not one standard deviation above the expected value of the mean. So it's pretty good. And that makes sense because the population mean was 8, and this is 8.07. So it's really close, right? So it's a small standard error. And so, like Kelly brought up, that's my point down on the last thing here. There's not, I don't know of a rule of thumb for standard error because it will depend on what you're studying and how many people are in your sample and how varied your scores are and all that stuff. But again, rule of thumb, smaller is better because it basically is saying, the smaller the standard error, the less these scores from your sample deviate from the population parameters, the more confident that you can be in that the statistic you got from your sample accurately reflects the population parameter, right? All right. Oh man, you guys, it's almost break time. Right, who needs a break before we move on to the next part, right? Awesome, okay. So now that we've gone through that information about standard error and we can look back on our definitions and hopefully they make a lot more sense now, right? So the standard error is in effect the standard deviation of the sampling distribution of some statistic, right? We saw that. And it tells us how much random variation we would expect from samples of equal sizes drawn from the same population. That's what it's telling us, right? And so basically, when we do this, when we calculate the standard error, it lets us know when I get a statistic based on the sample, how much error can I expect to have in this estimation? So what is the standard error associated with my statistic? And ultimately, it lets me know how much confidence I should have in my statistics. Yay. All right. That wasn't too bad, was it? All right. Do you want to do a 15-minute break so your brains can get ready, or you want to do 10? 10? Like, let's get done with this. All right, 7:10.
So we'll probably do this calculator for our next quiz.
I know. Yeah, let me.
I'm gonna make sure
I know. Look at that. This part's not so bad. I don't know why. I thought the Z, I don't know why, but I was like, Z scores are so confusing. I guess it's because we don't really use them that much in psychology. I'm just like, we don't do that.
I know.
We don't really do any of this. Oh, I guess I could pause Tegrity. All right. Now I can unpause Tegrity and be like, aren't we excited to talk about one sample test? Here, let's go over here. Okay. We just covered standard error. It's important. It's kind of awesome. It lets us know how much confidence we have that our sample reflects our population, right? So it's kind of cool little statistic that we can get. It's important because it lets us know that, lets us know like how confident, or gives us a measure of how confident we can be in the statistics we got from our sample. So it's important because of that, but it's also important because it's the last thing we had to cover before we can introduce get introduced to inferential statistics, which is, I know what you were all waiting for. So you're now, at this point, you're familiar with means and standard deviations and distributions, and we've even looked at some tables of probabilities, so we've covered some of that too, and we've talked about standard errors. And so so you have the foundation. We can look at significance testing and the ability to make inferences from our sample to our population. And so we're going to start by going over one sample t-test. And then we'll end class by talking more specifically about significance testing or null hypothesis significance testing. And so we'll talk kind of like about p-values and levels of significance and alpha levels and what all these things, how they're all related, what they do for us, and how we can interpret our findings. And it's very confusing, but we'll go over it. You'll have been introduced to it, and then you can kind of forget it. You can be like, my p-value is significant. That's it. We're good. I don't have to think about it much further than that. All right, so let's start with one sample tests. What are they? Why would we use them? How do we use them? Your book kind of just briefly mentions them. It's like, here's z-tests and t-tests, and then it like moves on. I want to cover them because you actually might encounter one sample t-test in especially a lot of nursing stuff, because it's basically when you are comparing your sample against a known value. So you already know like maybe what somebody's like blood pressure should be, and you can compare what your sample has to that value. So these are actually really helpful tests. And so they basically allow you to compare a statistic derived from your sample with a known parameter from either a population or a really large sample. So it's when you want to know if your sample is different from this already known value. So it's really basically what we were doing when we walked through the shoe example, right? We had this population parameter, and we had a sample of 20 women from Omaha, and we derived their mean shoe size from that sample. So if I wanted to know if the sample mean from my Omaha woman sample, if this was significantly different from the known mean, then I can use this one sample test to compare those values. So to compare my mean against the population parameter. And so that would tell me whether this is different. Like we can see that it's different, right? It was 8.07 and the mean, the population parameter was 8. But is it big enough of a difference to be meaningful? Is it statistically significantly different, or is it just because of random variation in my sample that we can ignore? So to do this one sample test, we would convert our sample mean to a score that we can compare against a distribution of scores to see what the probability of getting a random sample of 20 women with a mean of 8.07, what is the probability of getting that statistic from the sample if the population parameter is actually 8? So let's do this so that it makes more sense than what I just said. Like every time I hear myself talking, I'm like, that is a lot of words. But you'll be able to listen to it later, Friday night, hanging out with friends. You're going to be like, now that makes sense. So what's nice is this isn't the first time we've calculated a value from our raw score, right, and compared it against a table. A table of distributions of probabilities. We've done that before. We did that when we transformed raw scores to z-scores. We compared the score against the distribution of probabilities to see what percentage of scores fell below our z-score. But take a little bit of note to see how this distribution, this test is different. So with the z-score, we have one single score, and we were comparing it against a probability distribution to see what percentage of scores fell below it. That's what we did with our z-scores. What's different is like with a one sample test, you have a sample. So you don't have a single score, you have a single sample. And it consists of multiple scores, right? So like the mean of our sample. We have a sample, has multiple scores. We want to compare this sample, or really rather like the statistic we get from this sample. We want to compare our sample number or our sample statistic against a single number, like the population mean. So we want to compare our 8.07 against the population mean of 8, right? So the book mentions 2 tests that would allow you to do this, right? So it talks about the t-test and the z-test. The tests are really similar, but the z-test has a couple extra assumptions before you can use it. So the z-test basically assumes that you have the population parameters. So it thinks you already know these things, which you might, but the z-test mean, like, to use that test, you have to have the population parameter. It also assumes that you have a large sample size of at least 30. So if you don't have those things, you can't use a z-test. The t-test, just a second about why we would want maybe a more flexible t-test and a t-distribution. And we'll look at that in just a second. But basically the
reason we need a more flexible t-test sample sizes, right? We just talked about a lot of them. The population. So there are issues with small samples, not be that accurate. However, sometimes, so we might have a small sample, and even worse, we might have like a large variation in scores, right? But that's what we have. That's what we have to work with. So our stats from these small samples are likely to produce more or less normal distributions, right? They might be a little bit like more skewed or more kurtotic. So when we compare these values against a distribution that assumes we have a normal distribution, then we know that we don't get the most reliable information, right? We've kind of seen that over and over again. So to counteract the negative effect that we get from small sample sizes, we can use this t-distribution. And the t-distribution is awesome. It's similar to a normal distribution, but it's sensitive to sample size. So it actually fluctuates with sample size, and so it accounts for this number of people that you have in your sample. So the probabilities that are associated with the area under the t curve or the t-distribution, these take into account variation in sample size. So when you look up your number or your t-value in a t-distribution, you will see that the number changes depending on how many people you have in your sample. So basically, unlike the z-test, so here's our z distribution. Right here, it's like a normal curve. It always stays like this. But our t-distribution changes based on how many people we have in our sample, right? So here's a t-distribution when you have an n close to 30. So as long as you have almost 30 people in your sample, like we said, here's our normal distribution being approximated, right? So that's good. If you have a smaller n, the t-distribution accounts for that, and it has a different shape. And so it looks like is it leptokurtic? I can't remember. Platykurtic. Flat. So it looks like that, but it's okay because the distributions, the area of the percentage of scores that fall under each area of the curve account for that. They know it's going to look different, and so the probabilities are much more accurate. So it's good to use a t-distribution. Take home message. We want to use a t-distribution because it's flexible. It's robust to having a small sample size. It accounts for that, and it's totally okay. So it will give you accurate information from that sample. All right, so again, if we want to know if our sample mean differs significantly from a known mean, we'd use this one sample t-test and compare this mean against a population parameter. So to do this, we have to basically convert our sample mean to a score that we can compare against the distribution. So just kind of like the z-score, we have to convert our score to, we're basically going to convert it to a t-value so that we can check our value on this distribution of t-values. So here are the formulas for doing these conversions. The top formula, this is the one we use for a z-test, and the bottom formula is the one that we would use for a z-test. And you can see the real only difference between these is
what is underneath them, right? So this assumes that you know the population parameter and the population standard deviation. The t-test thinks that you are going to estimate this based on your statistics, based on your sample. So this is the one we want to use. So again, let's go ahead and kind of ignore the z-test because I won't have you do a z-test. I won't ask you questions about z-tests. I will only tell you about t-tests because they're so flexible. I don't know why you would never not use them because you can basically use them with anything, you know, like with any sample size. So again, if we want to know if our sample mean is statistically different from the population mean, the first step is to convert our mean into this t-value. So we'd use this formula, calculate the t-value associated with our sample statistic, and then you use your score and your degrees of freedom based on your sample size to find the probability associated with the t-value. And this t-value will basically determine the probability of having a t-value of that size by chance. So basically what we're going to do is calculate the t-value, look it up on the distribution of t-values, and see what the chance or what the probability of getting that value by chance is. Okay, we'll walk through it, but that's basically what we're going to do. All right, so let's walk through it as a group, and we'll use pictures, and it will become more clear as we go. So we'll calculate the t-value, the degrees of freedom, and then we'll compare these against the t-distribution all together so we can see how you would do this. So here we have our known population value, right? We have our mean, our population mean of 8. We know this, we already had it, we've already seen it. And then we also have the information from our sample, right? So remember when we looked at the distribution of scores calculated from SPSS, we had like our mean of 8.07. These are the same values. So basically all these little white bubbles are all these ladies' shoe sizes. So these are the 20 ladies' shoe sizes. We calculated the mean. We calculated the standard deviation. We have our N of 20. There's 20 of them. And we actually already calculated the standard error, right? We all did that. So that's already all done. So we have all this information. And here's our formula for the t-value. And you can see to calculate the t-value, you need a couple pieces of information, right? You need to know the mean of your sample, you need to know the mean of the population, and you need to be able to divide it by the standard error. And by mean of the population, it's basically the mean of the thing that you're comparing it against, the number that you're going to compare it against. But yeah, basically you need the mean of your sample, the population mean, and the standard error. And here's all of that information that we have right here, right? So if we actually plug these numbers in and calculate this t-value, we get a t-value of 0.16, all right? Anybody have any questions on how to calculate this? I totally get it. You know how to add and subtract and divide and multiply. All right, so we have our t-value. The next step we have to do is compare this value against a table of probabilities to see what's the likelihood of getting a t-value of this size by chance with a sample of this size. So we have our t-value that will help us. The other thing we have to get is this thing called degrees of freedom. So you don't have to know a ton about degrees of freedom. Basically, like suffice to say, degrees of freedom, they have to do with having enough pieces of information to calculate your statistic. So again, you won't need to be terribly familiar with that. But we have to be able to calculate degrees of freedom, and they're based on your sample size. And so to calculate degrees of freedom for this test, it's sample size minus the number of groups. And we only have one group, right? It's a one sample t-test. So we have one group, our sample, and so it's basically n minus 1. So we have 20 people in our sample minus 1. So our degrees of freedom is 19. Are there any questions on that so far? It's all going to come together in a second. So we have our t-value of 0.16. We have our degrees of freedom of 19. Now all we have to do is to compare those pieces of information. We can use them to find our t-value, our critical value associated with our t. So your t-distribution table can be found in Appendix B on page 187. I found one. It's a little fuzzier than the last one, so I'm sorry about that. But it's the one that looked the closest to the one that you had in your book. So we've seen a distribution of probabilities table before, right? Like the z-table. But this table's different, right? It's actually quite a bit different. So with the z-table, right, we had our z-score values on the columns and the rows, and the number that we found that intersected those, it was the percent of scores that fell below the z-score. That was the z-distribution. In this table, you have your degrees of freedom on the side, right? And across the top, you have these p-values that will let you know if the t-value you got was statistically significant. And you'll see that there is different values for having a 1 and a 2-tailed test. And we'll go through that a little bit more in just a second. But basically, if we walk through this just a bit, we have 19 degrees of freedom, right? So let's go to our 19 degrees of freedom column, right, or row, I guess, right here. Actually, look at that. It's like, I think I planned ahead for that. All right, so here's the column of t-values associated with 19 degrees of freedom. I have a one-tailed test, but basically that's because I'm pretty sure that my sample value is higher than the population mean, right? Like it's 8.07. I'm pretty sure that I am testing whether or not it's higher than the population. If I wasn't sure, I would have to say, I think maybe it's different from the population. I don't know if it's higher or lower. So I have to have a two-tailed test. I have to test whether it's higher or lower. But I'm pretty sure that it's going to be higher, so I'm doing a one-tailed test. I'm just testing whether or not it's higher. We'll talk about this a little bit more too when we look at p-values and stuff, but just so you know, we'll walk through this way first, and then we'll get into that. So if we follow along the line of t-values for 19 degrees of freedom, we can see that the numbers get higher towards the left, right? So they're low here. They go up to 2.861 the farther left you go. And they get increasingly lower towards the right? Okay. So what we're looking for here, we're not looking for our t-value. So that's what's different, right? Like in the z-distribution, we were looking for our z-score. We're not doing that here. Here, we're looking for where our t-value would fit. So we go to our 19 degrees of freedom column and we try to find out where our t-value would fit. So, for example, if I had a t-value of 2.25, right? 2.25. I can't find that exact value on the table. It's not on here. But 2.25 is bigger than 2.093, right? And it's smaller than 2.540. It's in between one of these two, right? So it's right around here. And once I find where my number would fit on that line of degrees of freedom, I look up at the top to see if my t-value is significant. So if I have a t-value of 2.25, I can't go here because it's not bigger than this. You want your t-value to be bigger than this critical value. These are called your critical t-values, and we'll talk about these more in a little bit too, but just to kind of introduce this. So my 2.25 is bigger than this, but it's smaller than this, so I have to go with this column. This is where it would fit. And I look up at the top, and here's my one-tailed test, and it says 0.025. This is the p-value associated with my t-value with 19 degrees of freedom for a one-tailed test. That's a lot of information. But basically, this is less than 0.05, right? 0.025 is smaller than 0.05. So this means that it is statistically significant. So when people are like, P is less than 0.05, that's what they're talking about. And we'll talk about this more when we get into the p-value section as well. But just to, again, to kind of introduce this stuff. So this is what the t-distribution table looks like. And I wanted to walk you through that because it's not the same as the z-distribution. It's way more confusing, I think. So, so here's our t-value. You have to meet these critical values. Once you have your t-value is bigger than one of these, you map it onto where it would fit, and you look up and you see if it is significant, if it's less than 0.05. So that's if we had a t-value of 2.25. But what is our actual t-value? It's like 0.16, right? So let's look for where that would go. It's like way over here. Like it is off the charts. So basically, what this is saying is that our t-value is really small. It's really small. In fact, the smallest t-value on this table, right, associated with 19 degrees of freedom, is 0.688. It's way smaller than that. So it'd be way over here. And even if we looked at this value, so like it doesn't meet this critical value. It's not even this good. It's really small. If we even looked at this value, like which is way larger than ours, and we look up here, the p-value associated with the one-tailed test for that p-value is 0.25. That's way bigger than 0.05. So that's saying it is not significant. Because if p is less than 0.05, it's significant. If p is greater than 0.05, it is not significant. Yeah, no problem. I know, like it's really confusing. So your p-value you want, so here's your t-value, it's your critical value. So it has to be bigger than this. It's not bigger than this. But even if it was 0.688, if we looked up, even if our t-value was 0.688, if we looked up for what the p-value associated with a small t-value like this is for 19 degrees of freedom, if we looked up, we would see that the p-value for a one-tailed test is 0.25. And that's way bigger than 0.05. And so we determine whether something is significant or not based on whether the p-value is less than 0.05. And so if this value is bigger than 0.05, it's not less than 0.05, so it's not significant.
Is there a slide that says this?
I hope so.
Oh, wait, yeah, it's the next
Okay.
one.
I was like, the next thing we're going to talk about are these p-values and null hypothesis significance testing and all this stuff. But your book just kind of dives into talking about critical t-values and the t-distribution. And I wanted to kind of walk you through this table because, again, it's really not as nice and easy as the z-score. It's much more confusing. So you're not looking for your t-value. You're looking to see if it meets this critical value associated with this level of significance. And so my t-value of 0.16 is not meeting this critical value, right? It's way smaller than what it needs to be even significant at the 0.25 level, which is not good enough. And it basically just means that my t-value is not large enough to indicate that there is statistically significant difference between my sample mean and my population mean, right? So it's not, the difference is not statistically significant. And if you think about it, it makes complete sense, right? Because my sample mean is what?
8.07.
Right, and my population mean is 8. So they're not different. So basically what doing all of this has said is that my sample mean is not significantly different from my population mean. It is very close to the sample mean. So if you want to interpret that one way, you could say that it's not that different. It's probably pretty close to the population mean. It is not significantly different. It's pretty representative of the population.
So if the p-value is less than 0.05, there is a significance.
Yes. And it's
If
very,
greater, then it's, there's no significance.
Right. That's our little rule of thumb. Is P less than 0.05, we all celebrate. P 0.06, we cry a little bit. And then we say, it's approaching statistical significance.
Repeat that again.
So there's no
Yeah.
significance in this one.
Right, there's not. If we have a t-value of 0.16, it is not significant. And if you look further, the bigger your sample is, the smaller little t-value you need to get that. And that's because we have lots of benefits of having a large sample. But this is to infinity. Like, if you have an infinitely large sample, you would still need a critical value of 0.675, and ours is 0.16. So it's basically saying our sample mean is not different from our population mean. They are basically the same.
So we always look at the one tail, we never look at the two tail numbers.
So we'll talk about that. So you look at one tail if you think you know the direction of effect, meaning I thought my mean for my sample was bigger than the population mean, right? So I thought 8.07 was bigger than 8. So I just tested whether it was bigger than 8. But if my question is my sample mean different from 8? It could be bigger, it could be smaller. So we have to test it at both ends of the spectrum. So you use two tails for that. Most of the time you use two tails, honestly, but if
The rule, then we can go.
yes, and we'll go over all that right now if you want. But okay, yeah, so if this p-value, if it equals 0.05, the beauty part is too, again, people don't use these tables. These tables are very confusing. They're nice, like, to kind of wrap your head around what's happening here so you can see, like, this is a critical t-value with this many degrees of freedom. It's associated with this level of significance. It's not significant. Your SPSS output will say, here's your t-value, p equals 0.79, way bigger than 0.05. And it even flags it. It puts a little asterisk by it if it's significant. It's like, hey, it's significant. Why don't you go look at your t-value and your p-value and see how great you did? But yes, so if p is less than 0.05, it's significant. If p is even 0.06, it's usually considered not significant. Every once in a while we make a little exception so that p can be up to 0.10. And when we interpret that, we say it's approaching significance. So every once in a while you can get away with saying like, oh, it's suggesting there's a relationship, but most journals are like, no, you can't. It's not less than 0.05. And we'll talk about, right now, let's talk about why that is. So I am sorry that this is so confusing because I was trying to think of the best way to present it, and I was like, no matter which way you go, it's confusing at first. So we dove into a one-sample t-test because your book presented that first before talking about p-values. So I wanted to walk through that a bit more, introduce you to this table, and then let's look more at this whole realm of null hypothesis significance testing. And that will encapsulate all of this stuff that we just did and will hopefully shed some more light or maybe confuse you some more about what all of this stuff means. And again, if you're still a little confused, it's okay because most people will tell you that having a p-value of 0.05 means that there was a 95% chance that you found the statistic in your sample and it really exists. And that's not exactly what it means. It's much less intuitive and confusing than that. So most people don't really actually know what it means. I'm still kind of wrapping my head around what these mean. But so at least know that, that you're not the only one. All right, so we just have this crash test, crash introduction to one sample t-test, right? Your book presented them first. I wanted to cover them. We also talked about critical t-values. That's these guys right here. We talked about levels of significance and p-values. So we kind of got into this, and it's a ton of information to take all at once. So I wanted to now take a step back and look at what we did and examine it through this format of significance testing, or what other people call null hypothesis significance testing, or NHST. So if you ever see that, that's what they're talking about, null hypothesis significance testing. So we have information, so let's take a step back. We have information from our sample. But as we said in the last class, we're not really interested in the average shoe size of this sample of 20 Omaha women. We get the statistic from our sample. We want to infer. We assume it's telling us something about the population. So we can make inferences based on the information from our sample, push it onto the population, and better understand the population. But as we just saw, if we're randomly drawing samples from the population, every sample we choose will likely have some random error associated with it, right? And so we use these guidelines from the central limit theorem, and we can be pretty sure that if we have a decent enough sample size, our sampling distribution will follow a normal curve. And because the sampling distribution has stable mathematical properties associated with it, we can use the standard error to calculate the probability of obtaining a sample statistic from a sample of a given size. So basically, we can use the standard error to see how confident we can be about the statistic we got from our sample. But as we also saw with the one sample t-test, we can also use all this information to test whether our sample statistic is different from a population statistic or different, is statistically significantly different. And we can do this by using this pre-calculated probability distribution associated with our test values. And we can do it by comparing these critical values against a p-value, or the probability that the value indicates the probability value that indicates the likelihood of obtaining the sample statistic due to chance or random sampling error. So that's what we all just went over. But like I said, let's take a step back. And, oh, did I put there? Sorry. Meant to show you guys that one. Anyway, so let's take a step back and really look at what we just did and examine it through this format of significance testing. And let's start by talking about this p-value. What it is, what it means, how it fits into this whole picture of significance testing. So what is the p-value and what does it actually mean? Your book says that the p-value is the probability that you would get the mean that you got from your sample, given the assumption that your sample mean should not be different from the expected value or the population mean. So let's talk about what that means. So if our sample is actually representative of the population, we should get the same mean as our population, right? If it's really an accurate representation of that population, we should get a mean that's almost the same. However, as we saw, oftentimes we get values that are slightly different from our population mean, right? Because of this, we know some of the difference in our sample and population means will be due to random sampling error, right? We accidentally got some extreme people in our sample and it kind of moved our mean, because we know the means are really sensitive to outliers and people extreme cases. So we know that some of the reason that our means from our samples differ is because of this random variation, but it also might differ because of real differences, right? So what we need to do is determine how much of this difference is due to sampling error and how much is due to the actual difference between our sample and the population. And that's really where inferential statistics, significance levels, and p-values come in. So let's walk through this a little bit with our shoe size example. We know that our sample mean is slightly different from our population parameter, right? We've gone over that and over that. And we can see that. We can see that they're different. But by using inferential statistics and these rules of significance testing, we can tell if this difference in means happens by chance or is indicative of an actual difference. And so if this difference between the sample and the population is by random chance, we probably wouldn't find it in another sample, right? It will just have random variation. So if we took another sample, we probably wouldn't get 8.07 again if the difference is actually due to just random sampling error. However, if this difference was actually reflecting real differences between our sample and the population, we would likely find it in a few other samples as well, right? That have similar characteristics as our sample. So we might find it again. So what's nice is instead of having to do all of these different random samples, we can use the rules of significance testing, and they can help us to kind of figure this out, to let us understand how much of this is due to random variation and how much is due to actual differences. So let's go ahead and kind of look at how we go about doing this. So this brings us to our rules of significance testing. So again, it sounds a little tricky at first because significance testing actually works by comparing two hypotheses, and we find out which one has the most support. And what's nice though is our hypotheses basically reflect the questions we were just asking. Is this difference between our sample and the population, is this real, or is this due to random sampling error? So one hypothesis that we use is that there is no real difference between the sample and the population mean. So that's one. The other one is that there is a real difference between the sample and the population mean. So this first hypothesis, that there is no real difference between the sample and the population mean, this is called the null hypothesis. It's also represented as HO, H little o, subscript O. This is kind of our default hypothesis, that there is no difference. And so the reason it's like that is, like, in the sciences, the burden is on us to find support for this one. So we automatically kind of say this is, we automatically propose this one. And the onus is on us to find information that supports this one. But this is the default hypothesis. That's the first one. The second hypothesis is called the alternative hypothesis. It's also represented as H subscript A. So you can kind of think of it as ho and ha, I guess. It's more fun. But this is the hypothesis that there is a difference between the sample and the population. So as your book kind of notes, these hypotheses are typically laid out before you collect any data. So before you even begin your study, you usually have kind of thought about your null hypothesis and what that would look like in your data, and you've thought about what your alternative hypothesis is and what that would look like. And so before you even collect your data, you've framed your research question in terms of null and alternative hypotheses.
Can you say you mostly do the null one? Researchers mostly do the null one and not the alternative one?
They do both, but our default is that there is no difference. Okay. It's up to us to say, yes, there is. And so in the absence of enough support for this one, we support this one. Because we want to say, it's up to us to actually say, hey, this is different. And that's not so super important for you to know. But the nice thing is, science is based on having to find evidence and find evidence and find evidence. It doesn't start out by saying, this is true, prove me wrong. It's, this is wrong, prove me right, kind of a thing. Or this is not true, show me that it is. So it's really on us to show that it does, that it actually, there is an effect. And that's kind of to safeguard, so people can't just start proposing things all over the place. You actually have to show me that this is not the case. So that's why it's weird, because it's backwards. You're not proving this. You're rejecting this. So it's weird. And we'll keep going over that. But so before you even start doing anything, usually, you take your research question and you frame it in terms of null and alternative hypotheses. So let's just practice that a tiny bit. If my research question is there a difference between my sample and my population mean? For this research question, what is the null hypothesis? Is there a difference between my sample and population mean? Right, null hypothesis says there is no difference. There is an absence of the effect. My alternate hypothesis is what? Yeah, there is a difference. And so, although this null hypothesis pretty much typically takes this form of there is no effect. That's it. There's not an effect. Our alternative hypotheses can be a bit more specific, and this is where we get into our 1- and 2-tailed tests again. So you can basically, with our alternative hypotheses, you can do one of two things. You can keep it broad and general and say that that I just think there's going to be a difference. I don't know if it's going to be bigger or smaller. I just think they're going to be different. I'm not really sure how yet, but I think they'll be different. If you do that, you don't know the direction of effect, right? So you don't know if it's going to be bigger or smaller. You just think it's going to be different. And so you have to use a two-tailed test. Again, in the sense that you have to test for both types of effects, right? Higher and lower. You have to test for whether your mean was actually higher or whether your mean was lower. So if you don't know what direction of effect you think will happen, or if you don't have any specific idea of how it will differ, you just think it will differ, then you use a two-tailed test. However, we can be more precise sometimes. Like sometimes you won't know. Sometimes you won't know. You're just like, I'm trying to figure this out and see how my sample is different. But if you do know, you can also propose a more specific one-tailed test, right? Like we did. So we thought that our shoe size mean was higher. We wanted to see if it was significantly higher. So we proposed a one-tailed test to test whether it was higher, right? So this two-tailed test is testing whether it's different, could be higher or lower. One-tailed test is testing whether it is higher or whether it is lower, one at a time. So if you think it's lower, you can use a one-tailed test to test whether it's lower. That's it. If you think it's higher, you can use a one-tailed test to test whether it is higher. You can't do both. If you need to do both, you need to do a two-tailed test. This is the other thing that comes up. A lot of people usually do a two-tailed test because if you get some random weird variation in your sample and you think it should be lower and you use a one-tailed test and it's actually a little bit higher, it's over. Like your significance test is over and it's done and it's not significant. If you would have chosen a two-tailed test and it was higher, you could have found that it was significant. So usually people use two-tailed because it's kind of protective. It's like if it goes either way, I can see whether it's significant or not.
So should we just always use the two-tailed?
Pretty much. Yeah, pretty much.
You're like, now we need to think of which one.
I know, right? Usually we'll use a two-tailed test.
Like ethically, like you have like in your chapters or research or whatever, and you write these like the first chapter first. You know what I'm saying?
Right.
And
Where you're
then
making.
say whatever in your first chapter, you can't go back and say ethically you couldn't go back and just change it and say I'm using a two-tailed, right? Your research is done, or you have to or what?
What you would probably do is you would just see that it's in the wrong direction and you would just retest it. You would just be like, okay, well, I propose it's if you had written up this whole basis for why it should be higher and you found that it was lower, that's tough. If you used a one-tailed test, what you would probably do is just use a two-tailed test afterwards and be like, it was significant. However, it was lower. That's really contrary to my expectation.
So you just have to say what, you just have to be honest.
Right, totally. As long as you're accurately justifying what you've done, it's because that could be meaningful and interesting too. Like it was supposed to be higher, it's lower. Why is that? And oftentimes what you do in that instance too is you go back to your sample and you say what is it about my sample? Is it, are they typically lower than what I've seen? Because by that time you're really familiar with your area of research too. And so you know what typical values are. And so you can say wow, that mean was really low. I would have expected it to be a 6. It was a 4. No wonder it's low. If it was a 6, it would have been higher. So there's something about my sample. I probably got a non-representative sample. And again, as long as you can justify that and spell it out, it's meaningful. It's just in the wrong direction. It's just oh, that actually didn't work. Because that happened in my thesis and it was okay. It was just wow, I didn't expect that. Here's why I think it might be that way. And then you just postulate other reasons, based on some evidence you've read somewhere else where you're just actually this might be why that happened. And it's okay. You won't be able to publish it, but you will be able to graduate. So you can put it, that's called the file drawer effect. There's all these kinds of non-significant findings just sitting around somewhere that are meaningful, but nobody wants to publish it if it's not p less than 0.05. So, yep, that's just the way it goes. All right, so we framed our research question. Okay, good. We talked about these. And yeah, usually we just do a two-tailed test. The big deal is you're kind of spending your degrees of freedom when you're doing these tests. And so the larger your degrees of freedom, the less critical t-value you need to find significance. So I know it's like, is this too much information? So basically, if you do a one-tailed test, it only costs 1 degree of freedom. If you do a two-tailed test, it costs 2 degrees of freedom. That means your critical t-value has to be higher before you have significance. So sometimes people will do, honestly what I've seen people do, is if they did a two-tailed test and it was almost significant, so it was like 0.07, then they'll go back and do a one-tailed test in that direction and it will be significant. So it'll be less than 0.05 now.
Then you have to write about both of that then in your paper?
No.
Okay.
No. Honestly, most people would be like, yeah, I know what you did. You know, they're like, oh, you're doing a one-tailed test and now it's significant. And it's significant like at 0.03. I'm pretty sure that your two-tailed test had approaching significance. Yeah. So people do it all the time. You know, you would just go back in your article and be like, actually, I was always sure that it was going to be higher. That's just the way it is. So these are the two forms that our alternative hypothesis can take. Let's just go back real quick. So basically, whenever we are doing significance testing, we are proposing 2 hypotheses. No, the null hypothesis. There is no effect. That's our default. Right. And then the other one we pose is the alternative hypothesis. Yes, there is an effect, right? So in our shoe example, we could see there was a difference. Again, right, 8.07, it is different than 8.00. But like your book says, we're not trying to just see if it's different. We're trying to answer a deeper question than whether it's different from the population parameter. We're really trying to determine whether the difference between my sample and my population is statistically significant. Like whether the difference between my sample and my population means occurred by chance because of who I happen to get in my sample, or whether they occurred because there's some real thing happening that's making them different. So we know there's a difference. Now we want to know if this difference was large enough that the sample value was statistically different from the population value, right? So that's what we were trying to do. And as we saw in our shoe example, the way to actually test this, right? The way to like find out whether we have support for the null hypothesis that there's not a difference between them, or whether we have support for the alternative hypothesis that there is a difference between them. The way to find this out is to compute a t-value, to get the degrees of freedom, right? Compute the degrees of freedom, to compare these estimates against a critical t-value in our t-distribution table and see what level of significance is associated with that. And we have done all of that, right? So some of this is kind of straightforward because we've done that, right? When we completed the formula for our shoe size sample, we had a t-value of 0.16. We had degrees of freedom of 19. We used a one-tailed test because we thought our sample value was higher than the population mean. So we knew what direction of effect we were thinking about. And so when I'm looking for my t-value here, I'm looking at this critical value of t. Right? And basically what this means is that there is a predetermined critical t-value that my t-value has to meet to be considered statistically significant at a specified p-value level, right? That's what we saw when we did this. Did I have my, I took my green bar down. So my t-value has to be at least as big as the critical value here to be considered significant, right? We did that. And we looked at that and we saw that it wasn't. So when we look at this table, we're looking at the t-values that were associated with our mean, whether they meet these critical values to be considered significance. So I want to talk just a tiny bit about the p-values associated with critical t-values, so this makes a little bit more sense. So we briefly talked about what p-values are, right? And we said that these are the p-values really telling us the likelihood of obtaining the sample statistic due to chance or random sampling error. So if that's what our p-value is, how low should it be? And basically there's just this general consensus in the scientific community that the p-value should be less than 0.05. And so if our p-value is less than 0.05, it means we can safely reject the null hypothesis. That's what that p-value is meaning. We'll talk about it a little bit more too, but so there is just consensus that if our p-value is less than 0.05, we can reject the null hypothesis. We have statistical significance. Things are good. Let's talk a tiny bit about why this level is used to indicate significance, okay? So basically anytime that we test a statistic for significance, we're acknowledging that there is a certain amount of random error in this whole process, right? We're acknowledging that. So we're acknowledging that when we see a difference between my sample mean and my population mean, that it might be pointing to some real difference, but it might just be error that's causing this difference. And we want to do our best to minimize that error. And so although we acknowledge that there's always error, we try to limit that error by setting a p-value at a certain level. And this will set as kind of like, it'll be like a benchmark for helping us decide whether we can or cannot reject that null hypothesis. So this setting of the p-value is known as the alpha level. And setting it to be low helps us to reduce the likelihood of getting a type 1 error. So, in short, type 1 error means that we rejected the null hypothesis even though it was true. So we said that there was an effect and there really wasn't. The null hypothesis was actually true. So type 1 error means that we rejected the null hypothesis and it was actually true. So again, the null hypothesis is that there's no effect, right? And if we reject it, we are saying that the information we got from our sample suggests that there is a difference between the sample and the population. So if we reject that, we're saying there is a difference. There's an effect, right? But there's always a chance that the sample we have has extreme people in it, right, that are changing our sample statistics. And so maybe there really isn't a difference. We just got this kind of weird sample that's giving us this false information. So we just randomly got a sample that led us to believe that this sample had a different mean. So although we're seeing this difference between our sample and the population, this difference isn't actually really indicative of real differences. It's actually sampling error. So when this happens, we falsely reject the null hypothesis and we say that there is a real difference when there isn't one. So when we do that, that is committing a type 1 error. And that's bad, right? Because we're saying, oh, this happens, and actually it doesn't, you know? So this can actually be really problematic depending on what you're studying. You know, there's some things you study that it's okay to, like, you know, it's okay to make a mistake, like kind of what I study. It's not that big of a deal. But medical research, like, you don't want to say something works if it doesn't. Lives are on the line. So how all of this kind of works together is that our alpha level is the level of error that we are willing to accept. So if our alpha level is set at 0.05, that means that we are only allowing a 5% chance of committing a type 1 error. So we are only rejecting the null hypothesis on accident 5% of the time. So there's only a 5% chance that the statistic we found in our sample will be found statistically significant and will tell us to reject the null hypothesis when there actually is no difference. So that's what our alpha level is, right? It's this probability that we're going to make a type 1 error. So we set it low so that we don't make that error very often. And we can actually set it lower if we want to. right? Like we can set it at 0.01 if it's really important to not reject it on accident. We can set it at 0.001. It just kind of depends what you're studying and what your, what your field, what the typical level is in your field, and yeah, how important it is to not make a mistake, to err on the side of caution and say there is no difference. That's that. Sorry, I didn't find one. I gotta look deeper, harder, different. So we set our alpha level really low, so we reduce the likelihood of getting a type 1 error. And for our results to be considered statistically significant, our p-values have to be lower than our alpha level. So that's what the p-value has to be less than 0.05 so that we don't commit a type 1 error more than 5% of the time. So it's kind of a safeguard. So that brings us back to this table. When we try to find our critical t-value, that would indicate whether or not our results are statistically significant, right? Given our t-value of 0.16 with our 19 degrees of freedom. Oh, I really want that green bar to be there again. We see that in your table, the critical value would have to be 1.729. Oh, wait, no, is this a two-tailed? Oh, Alicia, why are you messing up these stats? All right. 0.1. Oh, okay. Maybe that's it. Two-tailed test. 19 degrees of freedom. There. Oh, that's why. I was like, why am I saying this number? Okay, so here's our 5, right? One-tailed test, p less than 0.05, so that we're keeping our alpha level low, and our p has to be less than 0.05. For a t-test with 19 degrees of freedom, that's a really horrible sound. There. Our t-value would have to be, our critical t-value is 1.734. Oh, I said one more down. Oh, thanks. 1.729. Integrity, it's 1.729. So if our t-value is larger than 1.729, larger than this critical t-value, then it would be associated with a p-value of 0.05, right? That it's less than 0.05. So that's good. Any of these are less than 0.05. So if our t-value is larger than 1.729, it's associated with a p-value of less than 0.05, which is less than our preset alpha of 0.05, so we're good on the type 1 error. So that means that there's only 5% chance that we got this t-value based on the information from our sample in error. So there's only a 5% chance that we got this information in error. All right, let's see. Yeah.
I think you said earlier, if you do the two-tailed test, you have to take off 2 degrees of freedom.
Like, so
So that would be 18, not 18, right?
right. Actually, so what's weird, sorry, I might have misspoke about that. It costs you degrees of freedom, but as you can see, like your one-tailed test is half the significance level of your two-tailed test. So like, if you're doing a two-tailed test and you have a value like, let's say, what is it, 1.729. If we were doing a one-tailed test, it's significant at the 0.5 level, right? 0.05 level. If we did a two-tailed test, it's 0.10, so it's not significant anymore.
And how do you know which one to use?
I would just pretty much always default to two-tailed.
Okay,
Yeah.
so for quizzing purposes, do the two-tailed.
Yeah,
We have to subtract 2 off of our degrees of freedom.
yeah, so that, I'm sorry, that's actually for something else.
You only do
No.
whatever it says.
Yeah, so you have your degrees of freedom. If you're doing a two-tailed test, yeah, sorry. So you don't have to do any other calculations other than finding your degrees of freedom.
Okay.
But part of what it has to do with is that it's costly to you in that it's easier to find significance with a one-tailed test than a two-tailed test, right? Because it's like half as much. So to find significance at a 0.05 level for a two-tailed test, your t-value would have to be 2.093, which is much bigger than 1.729. So you'd have to have a much stronger effect. Your means would have to be much more different to find it. But if your means are slightly different, you could use a one-tailed test and have a lower t-value and have the same level of significance. But basically, the only time you would ever use a one-tailed test if you for sure know the direction of effect. So if there's a question, it'll be like, if you know the direction of effect, can you use a two-tailed test? Or can you use a one-tailed test? Or when would you use a one-tailed test? When you know the direction of the effect. That's the only kind of question you would get. It would never be like, what does it do to your degrees of freedom or your significance level? It would just be, when would you use it? Okay, so we've covered all of this. Let's look, yeah.
Question.
No, that's totally
so
fine.
If the p-value is less than 0.05, there is significance.
Yes.
But we reject the null hypothesis.
Yes.
Okay.
Yes.
Right.
Yes, I know, I was like, this is probably the hardest class because this stuff is really hard to wrap your head around. After this, we're calculating statistics and we're like, is it less than 0.05? Good. Is it not? No. Okay. Then we can't reject the null hypothesis. But this stuff is really hard to wrap your head around. So if you don't totally get it, it's okay because you'll be doing some homeworks to try to get you to think about it, and you will start to get it as you keep going. But the first time you're introduced to this stuff, it's like, I don't even, I know, it's like, oh, I don't know if I want to teach about this. It's not fun. It's really tough to understand. But we're marching forward, and we'll do a lab, and we'll be back on the same page. Cool. Okay. So we've covered all of this now. Let's look at our t-value and its associated p-value. We determined that the p-value for our t-value of 0.16 is off the charts, right? Like our t-value, not even on here, right? Like it's like way over here. So the p-value associated with that is like 0.7, right? Like it's way not significant. So it's high. It's way higher than 0.05. It's higher than 0.25, which is the last thing on here. Like it's way higher than all of these levels of significance. And it basically indicates that our sample mean was too close to the actual mean, the actual population value, to be considered statistically significant, right? So we cannot reject the null hypothesis that there is no difference, right? We can't do that. We don't have support to do that. So again, take note that in terms of significance testing, we never say that we prove anything. We simply say that we don't have evidence to support the alternative hypothesis, or we say we can't support the alternative hypothesis, or we can't reject the null hypothesis. So all of the work we've done today about our sample and the t-value, all that stuff, although it's a lot of work, it's only telling a story of one sample, right? Measured one way from one population. So our work provides support for the null hypothesis, or it fails to reject the null hypothesis. It's not proving anything. We don't prove anything in science, really. We just gather support for things over time and over many, many studies, right? So typically you wouldn't actually report non-significant findings, but while you're learning how to interpret and report all these things, we'll just basically learn how to write up any finding, right? So if we were going to write up the results of our study, we would report it like this. The mean shoe size from a sample of Omaha women was not significantly higher than the actual population shoe size. And then you have your T, your degrees of freedom, your actual t-value, your p, and whether it was, and then it was greater than 0.05. So sadly, you have to remember greater and less than signs again. But you could also report it this way. So like you would have the same sentence here, but instead of typing this up, you could say T with 19 degrees of freedom equals 0.16, not significant. So that's what the little ns is. And notice that all of these little things, the T, the P, the ns, these are all italicized. So to report it in APA style, those have to be italicized. And so this is the exact formatting you would use. And it's nice you have access to this. You can just copy it and use that format over and over again. And again, I just want to reiterate that you would never report non-significant findings in reality. Like you would never report them in a journal, mostly because people might accidentally see that they might miss non-significant and they would see it as significant. So you just don't report things that aren't significant. You just report what is significant. But again, you're practicing, so we'll just report everything while you get in the hang of it. And the other thing to notice is that you indicate the direction of effect in your sentence. And I did, so like when you look, this is the same sentence, that the mean shoe size from a sample of Omaha women was not significantly higher than the population shoe size. So say the direction of effect when you report it. So you don't just say it was not significantly different because you did a one-tailed test. So if you did a one-tailed test, you thought it was going to be higher, it was not significantly higher. So you have to say that. All right. So we're basically done. Here's just some rules of thumb. The last couple slides are so that you can know these things. Your general write-up for your t-test results, you have your t, your degrees of freedom, your t-statistic, your p-value. And t and the p are italicized. There's another example. What's beautiful is SPSS will give you the actual p-value, so you don't even have to do less than and greater than signs if you don't want to, because they're kind of confusing. You can just say equals and say exactly what it equals. Yeah, if you have a one sample test, if you want to know the direction of effect, all you do is look at whether you thought your mean was going to be higher or not, right? So like if you thought it was going to be lower, the direction of effect would say lower. If you thought it was going to be higher, your direction of effect would be higher. So to find out what the direction of effect was, you compare the sample mean and that known value, right? So our sample mean was 8.07. Our known value was 8. So the direction of effect would be higher, right? If our sample mean was 7.85, then the direction of effect would have been lower. Our sample mean was lower. And yeah, usually like it says here, if there's not a significant difference, you basically just say that there wasn't a significant difference. So that is what you would write in reality. You wouldn't actually like go and report that, but I wanted to print it up for you so that you could see how to write it up. All right. Let's see.
I have another question.
Yeah.
I think I'm getting, I just want to make sure, so alpha is the golden 0.05. That's what we want. We want it to be less than 0.05 for significance.
Right.
So if the p-value is greater than that, doesn't that mean that there isn't a significance?
Yes. Yes. That is exactly right.
Okay.
Yep. You got it. Right? It's very twisty. The last thing to note is that if your p-value is less than your pre-specified level, then make sure you write that it's less than. And sometimes you can specify a really low alpha level, right? This alpha level would say that your chance of making a type 1 error is less than like 99.9%, right? That you have a 0.001% chance of making that error. But no matter how small your p-value is, so like if it's less than 0.001, you wouldn't report it as 0.000. You would say it's 0.001 if you're going to use these less than signs. I know, this is like all tangential information. So let's go do our lab and like actually work through one of these. All right. Oh, I was going to tell you about your article critiques too. We'll do it in the lab. Just like take a 5-minute break while we walk to the